Hello, this is Mr. Mitchell with a video on the nature of science. In general, scientists would say that the universe is governed by basic rules of physics. Now, we don't have to be out in space to be able to discover basic rules of physics, basic rules of science. Science is more than just knowing how things work. Science is observing, studying, and experimenting to find the nature of, well, things. Here's another slide. Over the years, scientists may perform experiments that build upon the experiments of other scientists. Here you can see scientists experimenting. Here you can see a scientist frustrated. Now, just because an experiment fails doesn't mean that it really has failed. Often these failed experiments lead to unintended successful discoveries. And I've got a couple examples of some people right over on the right side who exemplified that. However, you don't have to be a scientist and have some kind of fancy lab coat to do some kind of experiment. But you do kind of need to have the scientific thought in the process of doing so. But anyway, what has come from some failed science experiments? For example, over here there is this guy. His name is Alexander Fleming. And I'm using the wrong color. Alexander Fleming saw that a culture, you can see he's looking at a petri dish here, that a culture had an area that was free of bacteria. Somewhere there, just no bacteria whatsoever. So instead of continuing to follow through in his experiment about the bacteria, he changed the direction of the experiment and investigated this spot that had no bacteria whatsoever. And what turned out, that was a mold that was there. And that mold would become the first modern antibiotic called penicillin. So it wasn't what he was looking for, but it's what he found, which is what made science, which what made a discovery. Here, I'm sure this is an artist's depiction here, but here you have Wilhelm Röntgen. He observed a strange light a few feet away while working with a cathode tube. Here's his cathode tube. He's holding something else, but he noticed a light that was farther away than he expected. He thought the light would be near the cathode tube, and he wasn't exactly sure what was going on. But instead of ignoring the light and continuing to focus in on the cathode tube, he changed the direction of what he was investigating, and investigated where the light came from and what was going on. It turned out he had accidentally discovered X-rays. The light was having to do with X-rays, and he ended up winning the Nobel Prize as a result. Now, physical science has two main branches, and we're going to be in physical science this year. Physical science here has two main branches. You have chemistry and you have physics. These branches of science and other branches of science continually search for scientific knowledge that is called pure science. So the search for knowledge is pure science. Here you see George Washington Carver. He, like many other scientists, had that search for knowledge. In his lab and in labs of other scientists, they search for knowledge. They might even find something different from what they were looking for, but they are finding things. It's not just a matter of knowing science, knowing their results. It's having those habits of mind to where you could search for science yourself, the pure science. Now, technology is kind of hand in hand related to pure science. When we think of technology, we think of advancements like computers, which is true, but technology is the application of how science meets human needs. Pardon me. The application of how science meets human needs. And I don't know if you've noticed what I have here, This is something called the water wizard. The water wizard is where you can irrigate a field. You can see the spray here sending water out. You can irrigate a field just by touching something on an iPad or on a computer far, far away. And that's definitely using an application of science to meet human needs, not only the irrigation, but the technology to be able to put that on an iPad. The scientific method involves observing, asking questions, and something called skepticism. Scientists and science students should not just accept assumptions of fact that aren't backed by some kind of evidence. So, having this curiosity, not just ignoring things, but being curious about things and asking questions about them, and not just accepting what you've heard about those things, but investigating for yourself. You can see this guy right here is a little skeptical of whatever somebody is telling him right here. The scientific method involves observation and asking questions, determining what is known, investigating, interpreting results, and sharing. Here's the scientific method. Mentioned a little bit of it. A hypothesis is a tentative explanation for an observation that can be tested. In other words, a hypothesis is a guess. You can observe something. You can observe perhaps that all the red birds come to a feeder in the morning and not in the afternoon. So you can take a guess as to what is going on there, that the red birds may migrate somewhere else later on, that the red birds, well, whatever, turns out to be a guess as to what it is. So, but it's something you can test because you can continue to observe. However, a hypothesis, just because it's a hypothesis, doesn't mean that it's right. You could be completely wrong about the red birds coming in the morning because they're migrating in the afternoon. A hypothesis doesn't have to be right, but it's a start. You are taking a guess as to what might be true. Perhaps you can look around Coosa Middle School and come to the conclusion that, I think the smartest people in the school are the tall people. And that may not be right, but at least it's a guess and you can get some kind of data from there. Look at the grade point averages of all the students in the school and mark them, see how tall they are, and chances are in that case you would not find that true, but at least it's a guess. And from there, you can find out what is true. Because you don't really want to be limited if you find that it's not true. It shouldn't hurt your feelings. You just find out what is true. Now, kind of the next level after hypothesis is a theory. A theory is a hypothesis that has been tested and seems to hold true with all the evidence from repeated observations. What if you happen to test everybody in the school for intelligence and find that there is a correlation between the people who are tall and the ones who are the smartest ones? You could say you have a theory that the smartest people are the tallest people. It also doesn't mean that it's true. It might be true. There might be some kind of other reason for such a correlation. But it is based upon a hypothesis that has been tested and appears to be true. A theory must explain observations clearly. You can't just say vague things and call it a theory. You can't just say things in outer space have some kind of iron core to it. You have to be more specific than things in outer space. It wouldn't really be a theory if you're that general. Also, experiments that test a hypothesis that end up coming up with theories, they have to be repeatable. It's not something you can just take guesses at or it just stays at a theory. You must always be able to predict from a theory. For example, if your child becomes tall, they will be smart. And of course, that's probably not correct at all, but that is an example of a prediction that could come from that what probably is false theory. Now, the next level is a scientific law. A scientific law states a repeated observation about nature. Once you've tested that theory, once that theory's been tested by other scientists, and it still continues to hold true, we can call it a scientific law. Now, is it necessarily true if it's a scientific law? Not necessarily. We have had things that have been tested over and over and appear to be true, but are just true for other reasons. Let me give you some examples of laws of nature. There's a law of nature that is laws of nature can be described in words. Here is Newton's third law of nature. For every action, there's an equal and opposite reaction. That describes a law. A more specific way is in some kind of mathematical formula. This happens to be Newton's second law, F equals m times a, and you'll actually study and use that one in this particular class. These math formulas are what's called quantitative. These written formulas are what's called qualitative. Hey, I may have that wrong here. Quantitative, yeah, I've put it wrong incorrectly there, so ignore what I said about qualitative and quantitative. Anyway, these formulas are more precise than the word descriptions, especially when communicating them throughout the world. People who speak a foreign language may not can understand this, or the translation might not fully get what you would get with this F equals m times a. Theories and laws, of course, are not absolute. Scientists used to think that heat, for example, was a fluid that could flow from fire. That's what people thought, that fires were the origin of all heat. Now, of course, fires are the origins of heat. You can get a lot of heat from fire. It was called the caloric theory, and it seemed to be explained by this law. However, today we don't think that heat is the origin of all, that fire is the origin of all heat. We think that now we have movement is the origin of all heat. This is hotter because all its molecules are moving more. And hey, that's something we will actually talk about in this class. So after a couple of hundred years, experiments and observations eventually concluded that this was wrong, even though everything seemed to be right about that train of thought at one point. It just isn't what we think of now. We have models that often are used to help explain or even study science. Here's the model of DNA that you learned about in second grade, that seventh grade, that double helix right there. Here's the model of glucose, C6H12O6, that you have studied about before. But more than just little put together models helping explaining or helping explain science. Science use models sometimes to help with the experiment. It would be incredibly expensive to take cars and crash them all the time. So, excuse me, you have computer simulations which can crash the cars, and the scientists can look inside, or the engineers can look at these computer experiments and see what appears to be damaged and what doesn't. It helps as far as the real world expenses. Meteorologists often use models like this. So here's a model that predicts what's going to happen with the weather. Here it's predicting what's happening with these rain bands and with this front. Here it's predicting where a particular hurricane or some kind of tropical storm is going. Notice they're using several different models. Most of the models having it taken it toward Florida, a couple of the models having it taken it elsewhere. And that is just a good way to use models in which to try to figure things out. These meteorology models use wind speed, air temp, moisture levels, even the shape of the ground, all that data in which to come up with a forecast. Well, I hope you learned a little bit about the nature of science.